Recording. Okay, so I'd like to welcome Ralph Kaufmann, Purdue University, to talk on progress on operad-like theories with a focus on Feynman categories. Carry on, Ralph.
All right, so thank you very much. So now my computer has decided to put on the fan, but maybe you don't hear that. All right, so here's the plan. I'll leave that to be the plan. So the only comment is maybe that I don't know why, but I decided to start with a history. I think actually the reason was that I was told that this is also an opportunity to get people into the subject or to sell the subject. Then I need two disclaimers. The first one is there are people present here who already wrote histories, like Martin Marco in Marco Schneider-Stashev, which is very nice. And he also wrote this handbook article, which is a nice history. And so this is a brief, incomplete history with something skewed with what I need. And anything I need will be, you see, I'm using this Purdue logo, so anything I need will be highlighted in special Purdue gold. This is indeed Purdue gold. It's the right number. All right, so I'll trace the best, so let's go with the classical age. History should have some ages. And so in a sense, everything started out maybe from my point of view with props and pros, which were MacLean's. And I guess they existed in the 50s, but they were written down in 63. And they're special monoidal categories. So that's the first clue. And they're designed to help with higher homotopy. So that ties in with the title of the conference. This is next information. So they're special. What's special about them? The objects are just the natural number, and they're monoidal with the tensor product being plus. Then you have morphisms from n to m, because they're a category, so they have morphisms. And in more modern notation and other talks you'll see in hi, Jim. So I just said that you are the expert and I'm just, dilly-daddling around. But so. All right, so then the usual notation now is P for prop of n to n. So, and they have two flavors. That's another thing which we'll trace through the talk. They're either symmetric monoidal or they're just only monoidal. And in props, the P is for permutations. And that's basically it. And then, so then the homotopic aspects, so where did they come in? So the infinity here is important. So we have Stashev's A infinity algebras, which came from loop spaces and homotopic transfer. Then there's a paper by Boardman and Vogt about homotopy everything. So these were designed to help with higher homotopies. This is exactly the higher homotopies. And then there's something which is very important, namely the Gerstenhaber brackets in Gerstenhaber 63 paper, which from my point of view, and I'll take any hints if somebody wants to mail me some corrections. I'm happy about that. I don't want to discuss the history during the talk, but afterwards I'm very happy if somebody tells me I did something wrong. So this sort of for me is the beginning of algebraic structures, and that paper has a wealth of information. Then they were like precursors and related structures. And so Lazare had in 55 analyseur, and there were theories of Levin, which are also have this special basis feature that you have the natural numbers are there. And Lambeck introduced multi-categories. And they'll play some sort of role. Then the gold, I would call the next age the golden age. So we have Boardman and Vogt and May as principal actors. And there's continuing with this prop thing that we're looking at categories. So we have categories of operators in normal form. They introduced enrichment because now they looked at these categories as the morphism sets being topological spaces. They already gave a W construction as a resolution, and they introduced trees as an organization scheme. And then May introduced operads, and basically what you take is from the prop, you take just the N1 part, and he did two things. He made the morphisms into objects, and then had multi-morphisms, so in this multi-category kind of style. Then the symmetric and non-symmetric part is if these objects, the Pn1s, now have the symmetric group action or not. And so the classical thing you've seen also in what classical, I mean the May version of writing down these things, and then later the Markle version you've seen in the talk by Martin Markle, where you have these as a sequence of objects. And then this approach was very, I forgot to put in the EN algebras, the EN operad. So both of these things, in the new slides, there should have been an EN here. So maybe I'll try this now. So the point is that very importantly, you have the EN recognition and you have EN operads here, which do this operation, recognition for you. All right, then there was a conference called, I don't know what the conference was called, but the conference volume was called The Renaissance of Operads. This is also why I have a golden classical age. So the other ones I made up, but this is in the history books. So this was the Renaissance. And so I wasn't part of the Renaissance, but as far as I see the Renaissance, one of the things that actually came in was these links to physics. And basically, the new thing was that basically correlation functions. So functions, they're multilinear. And the OPEs, these are operatic. So that's how I see that. And basically, you can trace this also this connects with geometry now of moduli spaces for the first time. In master equations, the Sribas 93 paper, these were constructed by Kimura, Stasha, Voronov. You have BV and Gerstenhaber, so the algebraic structures interacting with the geometry. And BV, of course, like Batalin, Wilkowicki. And then this is in Kimura, Voronov, and Zuckerman wrote these things down. Then there's another input, again, where these correlation functions come from algebraic geometry in Gromov-Whitman invariance in quantum cohomology. There's a fundamental paper by Kontsevich and Manin in '94 on that. And then a little later, there's string topology, which also is a version of looking at string theory and correlation functions and having this this operatic content. And I should put it, maybe the operatic content was made more precise by Voronov. And then a last piece of input here from physics comes from Kohn-Kreimer renormalization. And so this also introduces, now what happened last time? Last time I could just do this. So now he doesn't let me do this anymore. So I cannot annotate anymore, but anyway. So let me go to the next slide then. So what I wanted to say is that this introduces Hopf algebras, and I wanted to write Loïc's Fossey's name there. All right. So then going on from that, so there is some in the, I don't know if this was part of the Renaissance, but this was something expanding the universe. So the operads were reconceived, and somebody can tell me afterwards if this is right. I could trace it back to triples in Getzler-Jones in '94. Then Ginsburg and Kapranov introduced Koshul duality, the Kohlbar and dual transforms. And they had signs which are shifts, and this is light gold. You can't see it. In a sense, this leads you a little bit astray in my point of view. It's better if it's, so this is good, but there's something off with it. The actual gold is actual gold. So then Getzler and Kapranov introduced cyclic operads. They did have sign twists, and they introduced this notion of odd cyclic operads, so that sign twists become more important. They're not just shifts anymore. And this links to cyclic homology and cohomology. Then another thing which I find extremely useful was Markuel's pseudo-operads. This goes back to Gerstenhaber 63, just the substitutions in one by one instead of having multi substitutions. This is important for the bracket. So you get back Gerstenhaber's bracket from this type of operad presentation. And for me, this will be a presentation of generators and relations. So there is something about these composition I products, which is smaller. So there is a smaller set of generators. And the other thing that got introduced here, and this will be important sort of for plus constructions later on, this is, I think, one of the first times where you have a unital and a non-unital version. The 4 categories always have units, but in this case, you don't have to have the units. All right, then there is again an expansion of the universe catching up with the fact that so geometric objects can also be surfaces. So we have, I think this one paper is a game changer, gets off with modular graphs, twists as high-power operads. It introduced the Feynman transform. There is actually something at the same time which is very interesting. So Schwartz also introduced modular operads and extended modular operads, and these are very important actually for the Gerstenhaber brackets in the master equations. So this is not actually Getzler-Kapranov, but the name modular operad is taken twice actually. Usually we go with Getzler-Kapranov, but this one by Schwartz is an interesting paper, which also has an interesting structure there. Won't get into that too much today. Then the other one is, but this is missing. So now I have to figure out how to, not actually, this is Kontsevich-Soberman. So again, this is a very important paper. So it has the fact that operads are algebras over a colored operad. It has a link to polynomial functors. It has a very nice sign formalism, and it introduces this minimal operad. So this extends the level of trees we have. All right. And then I call this the Baroque. And what happens is now we have more and more decorations and things that expand. So we have proprads by Valette, wheel props, half props, die operads, twists of these, colored operads in varied incarnations. And that one again, I'll be happy. So I wrote various incarnations because the history of those wasn't that clear to me. Colored props, again, various incarnations. Yao, Johnson, Hockney, and Robertson wrote books on this and looked at these things. So there are all these various beasts out there. And we also have interesting new operad examples. So the pre-operad is a very nice operad, which sort of isn't a leaf glowing operad on trees, but was an insertion operad on trees. So cacti are an insertion operad of sorts. The arc operad, and I'm a little bit prejudiced here. So this is stuff that I contributed to the zoo. I'm guilty. I made zoo animals. So this takes surfaces, and it was extremely helpful in proving various things of Kornkreimer's, proving the Linnaeus conjecture in various versions, linking up to Kornkreimer's Hopf algebra, linking to string topology. There's an open closed, and it links back to EN. So the thing was that this paper in particular, that's why I put this in gold, sort of said that you can, this is a string theory thing, it's not mine, but string theory says you can get higher dimensional object by looking at higher genus surfaces. It's a credo of string theorists. And this paper realized that. So you can have the ENs that go all the way back to Boardman-Vogt to get the higher loop spaces through May, and you can realize them on genus G surfaces. Now, there's some other notable things which I didn't know how to put into the list, but they're very important. So actually, these Plathism products, they are older. Smirnov and Joyal looked at them already in the 80s, and there is a way to define. So I think I said that. I think it also goes back to the Getzler-Kapranov papers to define operads as monoids with respect to this product. And also props and so on. So you can read that in the handbook article by Martin. So the homotopy theory, I think one of the seminal papers is the axiomatic homotopy theory of operads by Varga and Mordijk in 2002. So that is usually referred to when anybody does something with homotopy theory. This is the basic thing, and then it's expanded upon. There's something which was explained to me, and then tracing back the history. So this is basically the plus construction opitopes by Baez and Dolan in 97. And then Batanin had higher operads, which also added to the structure. And this gave rise to these operatic categories, which we saw in 2 talks already. All right, so the wish list So this is maybe a little bit of a personal recollection. So my point was I wanted to unify the zoo, including modular, hyper, and twisted operads, and I had seen nothing that actually did all of this. I did want to have a theory of enrichment, so that actually that was like for, which goes back to Boardman and Vogt. There should be a free construction, like you have free operads. I didn't mention this, but it's very important. And then one should be able to get the 4 ways of getting operads, namely just composition along trees, via generators and relations, so the Markle's operads, via algebras over a triple monad, and this is exactly where you need the free construction. And then the last one is via placism, which is this monoid definition. There should be a plus construction. There should be bar, Feynman, and Kovar transforms. The pre-Lie and Gerstenhaber should generalize to the full story. That should give us master equations like in Zwieback. There should be a homotopy theory. And this bar and Kovar should give us resolutions for the homotopy theory. And there should be something like the W construction going back to Boardman and Vogt. And then actually, the paper on Feynman categories in 2013 already has all of this. So everything is in there, and it's published a little later. So this is one of the curses. It takes forever to publish stuff. But in 2013, this was already in the paper with maybe, there's a second version, 2014, which had a little more detail, but it's been stable since then. And the only thing that wasn't there yet was this placism. So all the rest is already in that paper, and I can refer you to that. And this is a plug for my students. So we figured out how to do this, and where this placism comes in, it has to do with the plus construction. That's something new with Michael Monaco, but we have to write it up, and I don't want to give it away right away, so I won't say that much about it. But yeah, you should expect that in this year. All right, so so further connections. So the other things I had in the history that should be connected were this Hopf algebra of Kohn-Kreimer, and we succeeded in doing this with Ibarra Vez-Carrillo and Annie Tongs. There's a bracket missing. And previously we had to understand sort of all the examples. We gave something called decoration, or which turned out later to be a version of a Groten deconstruction with my student Jason Lucas, former student. And then together with Clemens Berger, we looked at this and found a nicer way which connects it back to Laver. And this is phrase and comprehension scheme, so that goes back to logic. And so there's a paper which I just recently wrote last year where the plus construction, and I'll say something about that, and algebras and modules and more details and applications are done. So they're very short in the 2013, so in the book Feynman categories, they're very short, and this gives an expansion. And so the newer results which are available are this more general plus construction. There's a construction of moduli spaces, which I'm currently doing with Clemens Berger, and there's a construction of compactification with Zuniga. And so this one has a new input. And these two, though, are actually sort of nice because they take what's there, all the methods we have, and they do computations and construct something concretely. All right. So let me relate this work to, the B means nothing, to other different approaches. So I wasn't the only one trying to unify the zoo or to understand what's going on. So this is by archive number. So the earliest thing was generalized operads by Borisov and Manin. And they sort of have an object based, like the May, I call the May definition object based because it's a collection of objects. And sort of this old Boardman-Vogt idea category based. So they went back to this May object based definition. And then Costello wrote a paper, and Getzler made this constructions precise in the notion of patterns. And these are basically category based. So we're looking at monoidal categories and monoidal functors. Then basically trying to understand these generalized operads and what's going on there, and using a category monoidal functor based approach seemed to resolve some of the problems or complications that arise in paper one. And this is how Feynman categories were born. In 2015, Batanin and Markle wrote down their operatic categories, and I also call them object-based, and they replace monoidal by fibers. Structures, yeah, this should be structures, but that's fine. I don't know what happens. Now I'm highlighted it. Cancel. Should be structures. So these are older, but they just appeared this whatever, like a week ago, last month. So just the end of last month. So they're moment categories by Clemens Berger, which also partially cover this idea that, how to put together several things, and especially the higher categories of Batanin. And you can view Feynman categories as links with theory. So a priori, these were different approaches. A posteriori, after being formulated and discussing with people, there were connections found. So as I said, there were generalized operads were the reason to look at Feynman categories. The main condition is modeled after the hereditary condition in there. We found out that after discussions, it wasn't that obvious in the beginning, but the point is that they're related to regular patterns. And we showed in the 2014 version that the hereditary condition is actually equivalent to the pattern condition. So the hereditary condition is something combinatorial you can just check. And this one is something which is a condition given on coends. So it's a little bit, uses a little bit more category theory, and is, in a sense, I would not know how to prove it unless you have the hereditary condition. And the relationship to groupoid category colored operads was already given in the Feynman category. And these relations were studied further by Batanin and Weber in 2015, so 2 years afterwards, and by Caviglia also 2 years afterwards. And so that gives the relationships between sort of groupoid colored operads and patterns and so on, exactly. And that leaves the other two candidates, operatic categories and moment categories, and they have a very interesting relationship. And it's in a sense what you would expect, because one is object-based and one is category-based. And the interesting thing is they're related by plus constructions. So together with Michael and Martin, we've been trying to make this strict in the case for operatic categories, and Clemens in his paper already said what the connection is. So he does a plus construction for the main moment categories and gets a Feynman category together with Batanin and Markle. So I have a plus construction. I'll say, sorry, we both have a plus construction, and then the point is that if you take a Feynman category, you can make it into an operatic category, make that into a Feynman category, and if you go around the circle, you get a plus construction. You could have done the same thing starting at an operatic category and going once around, you also did a plus construction. All right. So why Feynman categories, why do I still like them? So the point is they're just monoidal categories. So that's actually, they're fairly simple to write down. So that gives you symmetric and non-symmetric, exactly like pros and props. The monoidal functors just give you all types of operad-like theories. And they do give you the zoo, but because you're looking just at functors and just at monoidal functors, what you can do is you can do pull back and push forward and just have Kahn extensions. And one of the main things is, and that's what I'm doing with Clemens, is you can actually calculate these Kahn extensions. So it's not just an empty theory in the sense that, or what the homological algebra fan club calls abstract nonsense, but these Kahn extensions, you can actually compute them. And the hereditary condition is very nice because it's checkable. And I can give examples, and I'll do some examples. And all the graphical examples, so the things, so much of the zoo you've seen actually has one common root. There's just one Feynman category that does it all with decorations and restrictions. So there's only one thing you have to understand. And there's a nice interplay between all these constructions. And then something which is nice is, so originally I was after sort of the usual type of things, namely, props, operads, wheel operads, modular operads, you name it. But there's sort of a set level, which is one rung down, which comes also from looking at these ladders in the plus construction. And this set level gives you access to simplicial objects, and that also played a big role in this Hopf algebra thing. So there are two parts. The first part is about simplicial things and set theoretic things in principle. And the second part is about the categorical thing. So there's just one level lower where you can get even more handle on it, like we all like the simplicial category. I don't know. I can't see everyone, so I won't speak for everyone. I think some people here love this, like Andy, I can see him, loved it already. He shared the love with me. And so now I'm beginning to love it more and more. Before I was like, okay, yeah, it seems complicated. Monoidal categories seemed easier to me, but it works out. All right, so I think I said that. Well, I mean, let me see what's the time. Where's my clock? It's okay. So this decoration, you can think of it, if you think about graphs, it's like a vertex decoration, and the plus construction will allow you to do edge decorations. These things are fully functorial. You can push forward decorations, which is nice. And with Clemens, we get a factorization of morphisms for Feynman categories. So basically, you have covers, which are these decorations, and you have connected things. And I have an example where this is very pertinent. In the plus construction, that's less kind of complicated, but I'll give a preview here. So it has to be this complicated. That's why I wrote the 2019 paper. There is nothing simple about it. Unfortunately, there are three things. There is something, I'm sorry, I should say there is a very simple way to get this one. If you want to get enrichments or hyperoperas or the things you want, you have to do a little bit of massaging or inverting. But the important thing is that if you take now a functor so the decoration works like this. You take your Feynman category, that's a monoidal category. You take a monoidal functor, you get a new Feynman category. Direction works like this. You go one level up, so actually to the hyper level. You take a functor and then you go back down a level. And what you can do is you can enrich your original Feynman category with this functor. And this is exactly what gives rise to this Boardman-Vogt enrichment. And sort of the definition, when you look at the PMN, you think of those either as Hom sets or you think of them as functors, as props. That's exactly this thing. So, and then the FO ob, so the functors from FO let you define algebras. This is very much like the things you've heard in operatic categories. And the compatibility is kind of nice. So if you do the plus construction first, and then decorate, it's the same thing as taking this functor O, which is now from F plus, and then enriching, and then taking the plus construction. All right, so here the so what can you do? So these are the ladders. You start with an object, just a trivial category. You go up one plus construction. You get simplicial things. Then you get planar rooted trees. These are non-sigma operatics. Then you get nestings of these. These are hyperoperatic. You could start with an object in the symmetric version. So that's the non-symmetric version. This is the symmetric version. You get cross-simplicial, which is also known as non-commutative sets. Then you get rooted trees, which are operads. Then you get hyperoperads, which are nestings of trees. You could start the thing as cyclic objects. Then you go to planar trees and nestings of these. You could start with all graphs. And this is basically what gives rise to all these propic examples. Operad-like examples. You get nestings, you get hyperoperads. So in particular, you start with modular, you get hypermodular. The Grothendieck construction gives you this decoration. So you get these various types of graphs, with genus decoration and so on. And then the W construction is very nice. It gives you cubical complexes. And this is what ultimately leads then to moduli spaces. So you can take something combinatorial, make it topological, and then you're good. All right, any questions so far? Hearing none, I might say a little bit, but many people, I can't see everybody, but people might be bored by this because they've seen it. So if they haven't seen it, I'll go through these things a little quicker. So what a Feynman category? It's a symmetric monoidal category. I said I had a special property. One of the properties is it has sort of a base of objects, which is given by a groupoid. So actually the point is it's not only a base of objects, it's a base of the underlying groupoid. And this works like this. So you have basic objects which form a groupoid. You take the symmetric monoidal category on that. So this is still a groupoid. These are words in these elementary objects. And you have a functor here just by abstract nonsense. So this guy here is a monoidal functor. That's just a regular functor. That's the extension to a monoidal functor. And so now you have this triple. So F is your monoidal category, V is the basic objects, and this is the inclusion of the basic objects. And that's just a functor. I call it inclusion, but it doesn't have to be. And so then this monoidal functor gives you that the isomorphism, so the underlying groupoid of your monoidal category is exactly this groupoid, the free groupoid on the basic objects. And this one says that all the morphisms, actually the groupoid of morphisms, so these are just the maps in F together with diagrams which, maybe I should put this here. So the diagrams just look like you have like this. You have a phi here, you have an isomorphism here, and an isomorphism here. And this is an isomorphism going from phi to phi prime. So these are the morphisms in that category. And they're captured by simple morphisms, namely just ones that go from words to letters. So this one says this is words, and this one goes to letters. So this is written out here. So if I have something, the first condition says this is a tensor product of letters, and any morphism then which goes here, I can decompose the target as so X into its letters, and then the morphism decomposes into simple morphisms from a word to a letter. So that's exactly this condition, and this is just so that I can take colimits. All right, so it's fairly easy. It's a monoidal category which has a nice basis of objects and a nice basis of morphisms. Right, and then as I said, so now the diagram looks like this. This should be a Y. So from the previous page, I go to my X. I decompose this X as just some letters, and I have my phi here. And what I can then do, I can decompose this Y again. So the point is that this is in the same indexing set. V stands for vertex. I just got used to that. So the point is this is the same indexing set. And this is the tensor product of the phi v. So then the phi v, they go from your this yv to star v. So these are just basic morphisms. So in other words, in words, it's very easy to say every morphism up to isomorphism decomposes as simple morphisms. And that's the hereditary condition. As I said in the beginning, this is easy to check. So what you basically get is that gives you a pattern. So here's an example which we've also seen before, but there's maybe a little twist. So let's just take finite sets. We know that with disjoint union, that the vertices will be just the trivial category with one object and one its identity morphism. And if we look at the free monoidal category, we just take this one object and take disjoint union of it. And if you take disjoint union of one atom, you can get any finite set up to bijection. And that's exactly what this line says. I get every object up to bijection, plus actually, if I have an isomorphism of a set, if I look at the skeleton of this, so I'm looking then at the isomorphisms I can get, and then they're all governed by just the permutations on the set with n elements. And that's the free monoidal part. So if I permute these ones in this product, that's just the Sn action on this space, and that's enough to recover up to equivalence all the isomorphisms in finite set. So that's right. And then how does my diagram look? I mean, I have a map from a finite set to a finite set. I should decompose the target into its atoms, which I can do. And then I have to produce this decomposition of S, and I just take the fibers. So this is a very nice, and you see the fibers appearing naturally here as just a disjoint union of these fibers. And that's the decomposition into basic morphisms. And what should a basic morphism be? Well, a basic morphism has to be, I map my set to a one-point set. And it's very interesting, there are not that many morphisms of this type. Actually, there are actually only two types. If you think about it very clearly, either you have two cases, namely either you're mapping the empty set, which is okay, there's the empty map, or you just surject this to the one-point set. So there's exactly one map of this type, and so the fibers here are very limited. Either they're empty or there are sort of just sets, and then this disjoint union of these sets. And it's a little bit, you have to be a little bit careful. There's one thing where you have to think, if you go through this example, is I did include the empty fibers. So I'm tacitly doing this, and I can include the empty fibers. This will play a role. This has something to do with units. So actually, there are these two things. I either have surjections or I have injections, and basically the injections come from the fact that I can map the empty set to a point. That's how injections work. And then I have the surjections. So they're really these two parts. And we'll see nicely that we can disentangle them. The injections will just give us sort of units, and the surjections will give us sort of algebra structures. All right, so that's the set level. Then I'll do the example for the graph level. With that, I can put out all the sort of the zoo. I can tame the zoo. So to taming the zoo, so the point is the objects of these things are just corolla. So that's just a one vertex thing. And then I have stuff sticking out. So Sn, whatever, to Sk, and this S1. I don't have to order it. So this is just the set S. So this is sometimes just called star S. And so you can see that the set of these corollas is just finite sets, because that's a finite set. And the isomorphisms, I'm not making this up. There is actually, so one of the things which was great about the Borisov-Manin paper is they gave a nice version of graphs which does exactly what it's supposed to do and lets you keep track of everything. And so if you look at these things, they're valid graphs, they have isomorphisms, but it turns out if I just think about the set labels here, for this purpose, it's just exactly, again, my S, which was just defined in the previous slide, which is the free symmetric monoidal category on the trivial category. Then the objects of AG, so that's the second part. These are the vertices. I explained them. So the objects here are the disjoint unions of these. So I just call them aggregates. They're disjoint unions, and morphisms are graphs with an identification. So I don't have time to get into this Borisov-Manin version of graphs, which is very nice, but I'll give you a little overview. And this, so for the experts, you have to read the papers with all the bells and whistles, because otherwise it's not correct. There is extra data. So I make it sound simple now so that people who haven't seen it understand how I can go from graphs as objects to graphs as morphisms. But if you have your own favorite graph examples, you have to look at the details of this graph category to understand how it works. So there's some basic morphisms. So as I said, the objects are aggregates. So they're just these corollas, these vertices, which floating in space. And then what can I do? I can take two, I have to end up at a corolla for a basic morphism. And so I can take, so what are the generating basic morphisms? So this gets into the point about the circle I products. So this is exactly what does a circle I product, or in the unbiased definition, I take two flags S and T, I glue them together and contract this edge, and I get this guy. The other thing that's a basic thing is I take two flags S and T, glue them to an edge, and contract that edge back to just the vertex. Then the last thing I can do is I can merge. I can take two vertices and then just actually really merge together these two vertices. And if you're geometrically inclined, what this is this is a connected sum. If you take two disjoint surfaces, there is a way to view these corollas just as surfaces, either as planar surfaces or as just surfaces with boundary. And then this is just gluing and contraction of edges and surfaces, gluing of surfaces, self-gluing of surfaces, and this is the thing you would get from connect sum. All right, so where do the graphs appear? So the isomorphism classes in the connected case. So there are two things. They're fixed by the ghost graph. So connected and up to isomorphism. So those are important. So this is connected, that's not connected. And so here the first miracle happens. So these are just fine print for lawyers. I think I might skip over them. There's extra data if you have to merge vertices. There's extra data to actually add the local identifications to fix an element in this isomorphism class. But then something automatic happens, which is really nice. So composition, this is a category. It has a defined composition. I define an underlying graph. Automatically, without doing anything, I can look at what happens to the graphs. I take two morphisms, and I compose them. I can look at the graphs of these two things. So this one will be, I'm in the connected case, which means this graph will be connected, as you think. The second graph here will not be connected, but it's going to be the disjoint union of connected. That's this hereditary axiom. And then I can ask, what if I plug these two things together, what is this graph? It has to be a connected graph again. And how is this connected graph obtained? I take the connected components. They're indexed by the same set V. So that's the hereditary condition again. And I plug it into the vertex V. So this is exactly this type of Preely operation, or the type of operation which we've seen in the arc operad. So this is exactly this insertion. And I stress it again, this is not something that you define extra or have to do. This just automatically happens. It's a proposition. It's just what happens. So that I found exciting. So that's one thing which is great about this category. Here's a concrete example. So you have a bunch of vertices. You can take this graph. There is this identification with all these vertices. If I contract this graph, I'm left with the three outside tails. I call them tails. Some people call them legs, whatever you want. Some people call them half edges or flags. And I can factor this as a morphism where it's sort of, I take just first, I contract this bit. And that would, so I have to know which vertices these are. So what I'm explaining is everything is labeled. So there's U, V, and W. I contract them to a new vertex R. I don't do anything to these two corollas. And then I just move. And then the next time I take the graph here, what I get is then I have these three vertices and I contract those. So you see, this is kind of nice. And this is also important. So I'll say this again. There is like a dual picture here, which actually is very important also for the Hopf algebra thing. There are two ways to read this picture. Either I look at it as a composition, which I described to you, which is plug in the graphs into the graphs. And this is where you need the hereditary condition, or that's exactly what the hereditary condition guarantees, that what this picture suggests to your mind is true algebraically, computably. And the other way to look at this is, well, I could take this, and as I explained it, I said I break it into two steps. And that basically is a coproduct. That's the underlying thing. So that's the underlying thing for the Hopf algebras. And this is also very nice, because what does the categorical approach buy me? It automatically buys me a coproduct structure, which is I take a morphism and factor it. There's something more going on because the factorization, see here, this thing goes to just a basic object. So there's something fun going on here, that I have these kind of terminal-like objects. They're not terminal, which are these stars. And so when I look at morphisms, I decompose them. And then one part, it's actually a co-module, will be exactly these basic morphisms. So I explained the Hopf algebra in a co-module just by looking at that. So this I already said, contraction of subgraphs. So, and if I want to look at factorizations, what I can do is I can contract subgraphs. So this is very nice. This gives you the duality that's been noticed many times for these graphic examples. Either you insert stuff or you contract stuff. So composition is insertion, decomposition is contraction. These are the subtleties, which I did mention. And all right, so then take a breath. So these are these examples. And now where does the zoo come in? So this is the basic code, the genetics, if you want. They're these combinatorial things. They're these graphs. And how do operads and operad-like objects come in? They come in through functors. And again, this is why I like the categorical approach. It's a category. I just look at a functor. It was a monoidal category, so I should look at a monoidal functor. There are two pieces of data which I have. I have my monoidal category, so I look at monoidal functors. And if I look at strong monoidal functors, and if I'm symmetric, I look at symmetric monoidal functors. It's easy if I'm not symmetric, I don't look at symmetric monoidal functors. I just look at monoidal functors, but the strong will stay. One can do lax. Actually, that's part of one of the constructions I don't have time for, but if you replace strong with lax, there's yet another construction which gives you a Feynman category so that the strong monoidal functors out of that one are the lax monoidal functors out of the underlying one. Then the second piece of data were just the basic objects, and they will be V modules. Sort of, this is just a category. It's actually groupoid, and is this on this slide? Maybe to cut the expectation. So the F ops will be operads. That's why they're called ops in a sense, and the V modules are the S modules. So that is sort of this nice way of thinking about this collection of the ON with the SN action. This is the V module, and then the actual operad structure on them comes from the fact that they come from this functor. And then the compositions are just from that functor point of view. One thing is very important. There is the trivial.
There's a couple of questions in the chat.
Okay, yes. Let me try to see the chat.
So the phi cubed you had, was it the previous slide? So Jim says, is that Konkheimer?
Let me see if I can, I don't know where my menu is. I sort of, because I'm screen sharing, I can't see the chat.
A couple of pages ago, just where you had the phi 3 with the diagrams.
Right, okay.
So the question was just, is that phi cubed Konkheimer?
That is phi cubed Konkheimer. The Hopf structure on this.
That was my question. I thought I recognized the diagrams.
Yes, this was for talk for Dirk. So yes, indeed. Other questions? And seriously, because I'm sharing from my iPad, I cannot see the chat.
Yeah, let me just read from Dominique. Insertion versus extraction contraction. Is the role of symmetry factors fully understood in this duality?
Yes. The answer is yes. The answer is complicated. So this is in the 2 parts of the Hopf algebra paper. And if you look in the first part, there is a sections about that which deals with these symmetries.
Fine, thank you.
And we can discuss afterwards. It's not that easy, but you can do it.
Yeah.
And also in the second part, you can do the categorical symmetries. You can work with the groupoids, but again, it's not easy. Yeah, part of it, I make it sound easy here, but if you look at the papers, unfortunately, they're very long, but this is unavoidable. That's the unfortunate part. If you want the results to be strict, they have to be a little long. Other questions? All right. Moving on, so let me just do a little fun example. So you might see a difference. So we had this finite sets. Maybe I'll just do surjections, and I claimed I'll get algebras out. So this is kind of nice. So what is it? So if I have a monoidal functor, I only have to know it on the generating object, which is 1. I call the value of that functor O is just a functor. On the generating object, it will be something in C, in this category, in the target category C. And then I'll call this A for algebra. Then ON, because it's a monoidal functor, I know that this is up to isomorphism, but that would be equal, make it strict. Then it's A tensor N. So that gives me the functor on objects. Now I have to figure out what the functor does on morphisms, and I already sort of discussed that basically. So I just have to, no, I didn't discuss it yet in full detail, but the first morphism is just a surjection from 2 to 1. That will give me a map from A tensor 2 to A. That's a multiplication. Then there's something nice actually, because I only have the surjection, so I did mention that if I want to go from 3 to 1, there's just one map, but there are 2 factorizations of this map through 2. So I first contract, actually there's nice trees associated to it. So I start with 3 things, and then I can contract 2 of them and keep that guy and then contract them. Or I could do the opposite and contract those 2 first and do that. And those 2 things have they give me the same morphism here. The morphism here is the same. It's just contract all three vertices. So if you want that morphism, it's just this graph. And so what you get is that because this is a functor, so because that's the same morphism, this map here has to be this map and this map. So you see that the product is actually associative. And if I'm in symmetric world, I have the A tensor 2 has a self-action. So I can flip the two factors here. This is just sigma 1, 2. And that doesn't change this map because, of course, there's only one surjection from 2 to 1. And if I precede it by flipping the two factors, it doesn't matter. So if I use that, then the product you see directly is commutative. And so that's a nice exercise. And if you don't do that, you get the ordered sets with order preserving surjections and associative algebras. And here's what I said: if you take finite sets, so the morphisms I didn't do now is the only other generator will be the one going from empty to 1, and this will provide a unit. So basically what I'm saying is if you go from empty to 1, then this will give the unit. So row of this map, it's called as I. The unit will be this row of I, which is an element in A, which is exactly a map from 1 to A, U. So that's really nice. So you get unital commutative algebras. If you take finite sets and injection only, you get Fi algebras, which are important for this Fi algebras and representation theory for stability phenomena. If you sort of add symmetries, you get the cross-simplicial groups. And so these are the skeleton of non-commutative sets. And we have an order on the fibers. So this is also something that many people found useful in the linear conjecture and other things. And they go back to cyclic objects, I think. I'm not quite sure. So Godet had the cross-simplicial groups, and then you can find them also in the work of Kahn as non-commutative sets. And here's the zoo. So I start with my Feynman category. Now I go one level up. So it's again about level. So this was level 0. I promise you get delta and order preserving surjection. So that's and then order preserving maps with fibers. So that's the set theoretical level. And then level 1 was the one that I was originally shooting for. And here it is. I mean, you just take the graphs and you put a initial condition on the graphs. And in the second step, I'll explain that also that is part of the whole magic, that is not willy-nilly. I mean, these are exactly those, the Groton deconstruction and the plus construction, and restriction at work. And you just put some conditions. If you just fix your graphs, those graphs to be rooted trees, you get operads, black and white rooted, you get multiplication, cyclic operads, unmarked, marked, non-commutative modular operads. This has mergers. You can get modular operads, which is sort of disconnected. And I guess this was somehow rediscovered now that the connected graphs play a big role. So this is, in one of the talks we heard, there's modular operads which have connected plus genus marking. And another nice thing is this genus marking is also for free from the, you can write it down like it was defined by Getzer and Kapranov, but you get it for free. You can do die operads, you can do props, you can do proprads, you can do wheel die operads, wheel proprads, wheel props. So all the zoo just is basically just saying one Feynman category of graphs, add some decorations, and maybe restrict. And so then I had these 4 things that I wanted to get done. One was, free functors. This is why the V is there and it's an important part of the data. I have a forgetful functor from my monoidal functors on this monoidal category F, just restricting it to the basic objects or pulling it back via the functor I to the V modules. And the first theorem we proved was that this is a junction, which is a junction of functors, but remember, these are monoidal functors, so there's something to prove. That you can take the free functor, that's a Kahn extension, and then you have to prove it's monoidal, and what you use is a hereditary condition, and then you also have the relation to patterns, which basically says this is a monoid, this isn't a junction. So that's why it's a good definition in a sense, but it defines what you want as an outcome. And the hereditary conditions gives you something to check that the outcome that you desire is actually happening. And so we get this nice thing. So we get this monad, we get this triple definition. So here is a little more detail. So you have these monoidal functors. So sorry, this is a more general version of this. I could look at functors between Feynman categories. Actually, they're pairs of compatible functors, but let's concentrate on the monoidal category level. I have a monoidal functor from one to another. I can restrict an op, so some other thing. And then what I can do is I can push forward doing a Kahn extension. And then the theorem says that this Kahn extension, so this will exist if the category is co-complete. And that's why I also have my slice condition. But the point is you have to prove that that thing is still monoidal, and you can prove it using the hereditary condition. And sometimes there's also a right adjoint functor, and that's part of a six-functor formalism. But that's nice. So now maybe I should say some examples here. It's like the prop generated by an operad, the restriction of a modular operad to its underlying cyclic operad, the free modular operad, what's called the modular envelope, and stuff like that. It's just now pushing forward and pushing back between these zoo. So it's really nice. It's all covered. And then, so this is the construction. So I'll do a brief overview. I have until 45, correct? That's what it said in the thing. So here's just an overview, and because then I have to select which ones I want to say, that's why I'm asking. So there is this these vertex decorations, how to get these things, the plus construction, which gives these hierarchies. They are important for the twisted modular operad. So if you remember my history, I made it a point that you have to figure out how to do the shifts for the bar and co-bar construction. And it's easy for operads. It's got more complicated for cyclic operads, and it got very complicated for modular operads. And this is where the twisted modular operads came in with Getzler-Kapranov. And since we have a plus construction, we can do this in general, modulo adding some additional structure, which is given by generators and relations. I won't have time for the non-connected version, but this is the one I mentioned that so that the FNC ops are equivalent to lax monoidal functors. There is co-bar Feynman, and we get master equations. I might flash those, or if somebody asks, I have an extra slide on that, and I would want to say something about the W construction. So let's start with decoration. It's what do? You have a functor. Now you look at pairs of an object and an element in the value of the functor at that point. So this is, if people know category theory, this is exactly a coordinate construction. And then what are the morphisms? They're the morphisms of the underlying category, but you say that the decoration has to go to the other decoration. Dec has to go to dec prime when you apply the functors to the morphism. And what are examples? So the point is, well, you have the Feynman category for cyclic operads. So these are trees, basically, as graphs. You take the cyclic associative thing, which is to this vertex S. It gives you all cyclic orders on S. So you see, these are just computations. There's nothing esoteric going on. And explain this. This is just a vertex with a set S. I can look at the cyclic orders. This is actually a functor. You have to compute this. And then you can decorate this. And what you get, well, I mean, at every vertex, if I fix a cyclic order, I fix the cyclic order. So that makes that thing planar. And so I get planar things. So I get planar cyclic operads. So this is what I'm talking about for free. So you have something which is sort of easy, namely cyclic orders, and you immediately get these planar graphs. They're fully functorial. I said that. So if I have a morphism downstairs, I can push forward the decoration, which was a functor. So that's where the Kahn extension comes in, and then I can decorate it here. It's also with respect to natural transformations of functors. It works out nicely. And we get on the level of operads, sort of ops, you get this complicated diagram of adjoint functors. But I sort of like one more than two. So this is what I'm sort of, again, advocating. If you go back to this Feynman category level, you pull it back to the encoding category, you just get simple diagrams. So this is this simple diagram becomes this diagram for the adjoint functors.
Can I interrupt again?
Yes.
Got a couple of questions in the chat. Jim, which master equation did you just mention? The master equation in physics?
Yeah.
And
I'll flash the slide.
Victor Carmona, does the decoration construction have something to do with enveloping operads?
No, the enveloping operads are the push forward.
Okay.
Well, so that's
say,
it.
when you said you had until
this is functorial. So enveloping enveloping sort of will be the push forward here. So this at F star and sort of the decoration is compatible with push forward.
Yeah. One other thing, when you said until 45 is when the next talk starts. So if you want any questions at the end.
Ah, okay. Yeah. So I read. Okay.
15
thanks.
minutes before that would be better. Yeah.
Right. No, sorry. Yeah. Then I misunderstood because I misunderstood the mail. All right. But now I see. Okay. That's what I thought. But okay. So then I have to go a little bit faster. So there's always a trivial decoration, and that gives you these minimal extensions, and that will give you a factorization system. But let me go through this. So I promise that you can now get this zoo by just decorating, and it's kind of nice. So you get directed versions by decorating by something. You get the genus marking by decorating with an N. You get colored versions by decorating with a colored set. You get non-sigma versions, which I discussed, by decorating with associative or cyclic associative. You get the non-sigma, this is sigma, not sigma, by decorating with modular associative. And this is kind of the modular associative is actually the push forward of the cyclic associative, so that will fit into a diagram. You can do dihedral like Brown, and because you have the dihedral operad. So this again just gives you everything from something very basic. And this is a nice example. So this is how this enveloping thing goes. I can look at the cyclic operads, and then I look at the connected. So that's important. So let me call that. Then I have this map down here. There's the inclusion. And the first thing is interesting is that if I push forward the trivial thing, I exactly get an operad here on the connected thing, and that's the genus marking. If I decorate with that, that's what I mean for free. You get modular operads for free. So the genus marking is just the fact that you have trees sitting inside connected graphs. You push forward, you get that. Then here you have to add that sets can have a cyclic order, so you can decorate with that. You can push forward the decoration and decorate with that, and then you get planar cyclic, and here you get non-sigma cyclic, which Mark Markle also found. And then you can do this for many other things, but this one here in particular is actually just the push forward of the trivial. Right, and this is, I just set those two things, it's calculation. Yeah, right, so again, I'll say that again, this is the genus thing is a calculation. It's not that I have to define something like you did in Getzler-Karpanov. It's the push forward. You can compute the push forward and the marking comes out. And you can do this in graphs, cyclic word, topological surfaces, or chord diagrams, whichever is your favorite, and then you get a flavor of thing, you know, a combinatorial theorem or something like this. If you like field theory, you get a nice adjunction. It tells you that TFTs and OCFTs are defined by Frobenius algebras, or they're defined by Frobenius algebras, which are either commutative or non-commutative. So that's an immediate consequence of that. So let me just flash the pictures of the W construction. There is a W construction, and maybe I'll mention that because I think also the talk after me will be on this. I just learned this here at this conference, you know, about these diamond conditions. I was completely ignorant, but the point is, you remember I had these graph morphisms, and you can contract with an edge E1. You could contract with an edge E2. You get different end results, but there is the image of this edge in the contraction that will give you another edge, E2 prime, and you can contract that, and the image of this E1 edge that will give you another edge, which is E1 prime, and you can contract that, and these things commute. It's a little bit difficult because these are not really the same edges, because these two sources and targets are not that aggregate is not this aggregate, because you keep track of everything. They're not, because this one lost those 2 flags at this one, and this one lost the other 2 flags. It can't be the same, but there's a nice way of saying which one corresponds to which. And that's the you have to formalize that, and that's basically what cubical Feynman categories do. And then in this kind of setting, there are 2 things which happen actually, and I'll have to abbreviate. So this setting will give you the differentials for the co-bar and bar. I'll say that again. So they give you the resolution in terms of co-bar and bar. And they also give you the resolution in terms of W, which then you can write down. And there is something, I don't have time for this, but here is a picture. If you do this, so these are, you can find those in the Hopf algebra paper. If you do this sort of on the algebra level, what you find is these nice pictures, which remind you of the bar construction for an algebra, and it is exactly that. But they're cubical, and this has something to do with the Cohn-Kramer differential. That's all contained in the Hopf algebra papers. You can see this has something to do with inserting stops. So with contracting simplices here, you know. The next one I want to do is sort of the isoscahedron, and that gets into this a little bit of the plus construction, which I want to get to. So I might have to go 5 minutes over because I was under the wrong impressions. But here's the plus construction. So you know these wonderful things, how to construct Stashev polytopes by cubical subdivision. And this is important because this is the W construction, and that gives you something cubical. And then you have to consolidate a few cells to get the Stashev polytope. These are the details. I'll have to skip those. But here's a nice application of this. So remember, I already constructed this. I can start with cyclic oprads. I can get modular, so the Feynman category for cyclic oprads. I can get the Feynman category for modular oprads by decorating, going through the connected guy. Now I could take the cyclic associative and push it forward. That was the non-sigma things. And now I throw one more thing into the mix, namely I can throw in the W construction. I can push forward and do the W construction. And sorry, this shouldn't be equal. That's wrong. So I should just apply that. Cancel. So sorry, this is not there. And so this is a functor. I can apply that to a point Gn, which are the objects in here. Those are the basic objects. And what I get out is the colon over the Kontsevich-Penner compactification, which contains moduli space. So really, I just have to remove the cone point. There's a cone point here, which is basically 0. If you do this, if you do the W construction first and then push forward, then what you get upstairs, then you get actually something nice, which is the nerve of the Guza category. So you just get moduli space back directly if you apply to this point. And then there's something nice if you do the Feynman transform of this thing and work in the algebraic world. I don't have time to do this, but you'll get, so this links back to the cellular chains on this compactification, which I was looking at with Bob Penner. The pretty pictures here, but let me not do those. That has something to do with Katkovsky and outer space. These are the master equations, maybe. So if you want to know something a little bit more, so the stuff with Zuniga, it basically has this problem. So you have the Kontsevich-Penner, the combinatorial, you have the linear Mumford, which you want to really have. In my historical overview, I said to get Zwieback, you have to use the Kimura-Stashev-Voronov compactification. So there's this tower of blowdowns. And together with Zuniga, we're looking at these things, and they're driven by master equations. And this is directly related to outer, the outer space of Folkman et al. Here's a nice picture of sort of this. I have to show this picture because it's nice. So I showed you how to get from a point the cubical construction to get an isoscahedron. So in the same thing, so this was very crucial when we're looking at the infinity of the linear conjecture. Unbeknownst to us, we used the W. It's not unbeknownst to us. I mean, we knew it was a W construction, but we didn't have the formalism in place yet. Did we have? But the same formalism I just explained gives rise to what we had there. So you see the cubes that are being, or prisms that are being glued on. And so from that, if you start with simplex, you glue on stuff and you end up in the cyclohedron, which we also see. So this was in the talk of blowups of this was the full blow up of the simplex in Joanna's talk. All right, so let me spend about 5 minutes on the plus construction. And so this was, I didn't know about this, but it was when in the beginning, so this was taught to me by various people, Martin Marco-Batanian and Clemens Berger, and it goes back to Bayes Dolan. And the point is, you kind of want to have this enrichment and get modules going, just like I had algebras and one modules over them. So just go back to simple stuff, which is going to be the set theory level. If I have an algebra, I can look at a module. We already know algebras are functors from the surjections. How do I get a module over that algebra? And the answer is use the plus construction. And there is such a thing. There is something, I already mentioned that there's a hyper if you do this. And that's why I looked at the plus construction. I didn't know about opitopes, but I was trying to get the twisted modular operads as defined in Getzler-Kapranov. And it's kind of nice. The same plus construction that gives me hyper, that's why they're called hype, not to hype them, but because they're hyper modular operads for the twists. That same plus construction actually is the same one as for opitopes, is the same one as from sort of what you, does the same thing you want for opitopes. And you can go play around with that and go one level lower. And if I start at the trivial level, I basically get surjections, and this will be algebras and modules. So the point is, how do I get algebras? I already explained that a little bit. If I start with a functor from the top guy, then I can enrich the original guy, and functors out of that will then be algebras. And I think the next slide makes that a little bit more detailed. So the objects of my plus constructions are just the morphisms. This is really nice. The isomorphisms are just the commutative diagrams I had before, just with isomorphisms on the what is that? I never know what that's vertical. Then the morphisms, and this is all in the 2013 paper already, so in the arXiv 2013, rooted forests whose vertices are decorated by morphisms and isos. And again, there is an identification with data compatible with the group-wide action. So when I say rooted forests, it's again, you have to use this category correctly. There's a second way by generators and relations, which is really nice, and that is the details how that helps you are given in the 2019 paper. And so there are versions. There's a basic version you can factor out by the group-wide action. Basically, if you do this plus construction, you'll see the morphisms twice. You'll see them here and you'll see them here. You can identify those. That's the GCP construction. And then if you don't want the isomorphisms to contribute, you have to do the hyper construction. So maybe let me just see what that looked like. So if you have graphs, you'll find exactly the picture that you also saw in Giovanna's talk. The point is, well, I mean, what are the morphisms become the objects? So the morphisms are just graphs. And so there's a graph sitting in here, and then you draw, so there are lots of graphs, gamma, gamma prime, there should be a gamma. Gamma 1, gamma 2, some other gamma 3. And you can think about them as having, you know, they go from vi to star v, so they're actually rooted. They look like this. So they're directed graphs. And what you do is you assemble them into trees. And here you put them gamma 1, gamma 2, gamma 3. And the way you put them, I need 4, I guess, 5, gamma 5. And then you contract these, contract the edges. And then you'll see this one has 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. And this one will have 1, 2, 3, 4, 5, 6. And basically you can compose, the point is they're morphisms along these flow charts. Again, it's a little bit more complicated. So you have this, and so there should be something here. Sorry, there should be something here in the gamma 6. You have to say which one goes where and how to identify the flags with these things, but it's just a composition. So it really is exactly these trees decorated by graphs. And it's, all right, so that's exactly this plus construction. So it's the one also that Joanna used here, the results. So these are, you can read these are from the 19 paper. This is FC's plus and representation theory. So if you start with the trivial, so this is again level 0. If you start with the trivial, then you get up this has ordered fibers, but basically you get surjections. So the ordered fibers will actually give you associative algebras instead of commutative algebras. If you mod out by this GCP, then you get non-commutative sets. If you do this again, so going to level 1, you take finite sets, you take the plus construction, you get operads. If you take the GCP, you get unital, so this forces units. Then if you do the hyper, actually what you do is you only get reduced. And so you see that, and these computations are nice computations. So again, I'm not making this up. You can read the computations, they're in this paper. And that so how does this now, that gives you enrichment in algebras, and let me briefly state that. So what you do is you start with your functors. If it's from this hyper, it says if you apply it to an isomorphism, you just get the monoidal unit. You keep the same objects, actually even the same groupoid of objects, but you enrich the morphisms. So for every morphism you had in your underlying category, you take O of phi. And maybe I should have even done the example. So this is exactly looking at this P and M. So this is exactly what Boardman and Folk did. So I had a morphism, just one morphism from N to M. And now I have a space of morphisms from N to M. That's the enrichment. This can be topological space. This could be a vector space of morphisms. But what you want is you want to be able to compose those. So the composition then will, there's some monodal functors again. So you take phi and psi to phi after psi. And this is exactly this kind of composition, which is given by the monodal functor. So this is exactly the point why you have a monodal functor. This gives you this transformation. All right, so that's nice. So what is the point? I have 2 more slides on this. There's always the free enrichment. So if you take the trivial functor on the plus thing, you get the free enrichment. So for each morphism space, if I go back here, you just put a unit, and that makes it enriched. So you take the free vector space over this set of morphisms, for instance. If it's an algebra over O, then as I said before, it's just something then which is a monodal functor, a strong monodal functor from FO. This should be an enriched functor. So if my O was like the vector spaces, then this should be a functor in vector spaces. Everything is enriched over vector spaces. You can do that. In the set case, it gives the relation to operatic categories and moment categories. So they don't work in the enriched settings. And at level 0, as I promised, you get a module over the algebra. So you start with this. That's an algebra is a functor from surjections. I already proved that to you. Then I can decorate with this, but that's just the category with one object and morphisms being O of that object. Actually, it should be C. Oh, so this is bad. This is bad form. Hold on. So this, let me call that algebra A, and this is then A. There are too many C's, and this is A is O of C, so this is A underline. And so that's exactly what a module is. You can, and if you do this for algebras or for operads, so you use that FinSet plus as operads, and then you already see also the connections to the other versions of taming the zoo. And sort of, then we can do deformations in Markov style. So you resolve O to O infinity, to deform the algebras over O, and you get FO infinity. So those are, and you can use the bar and Kovar description, which we had before, to give a resolution, or you could use the W construction in the topological setting. And here's the example. I mean, just use what I said before, namely that Fin plus is basically operads. Then you take your favorite operad, like the associative operad. That one you can W construct, you get A infinity. That was a picture of the Stashev polyhedron. And then I can enrich my thing. So I can look at fin set as infinity, ASOC infinity. And then I can look at the ops on that, and those are exactly the A infinity algebras. And I can do that either in the linear setting or in the topological setting. And so you get operad-like structures themselves. So you can do this at level, the next level up. You get hyper-operads and stuff like that, so you can resolve the hyper-operads. And I think I had a NB somewhere here. Yeah. So the disclaimer is I'm not talking about anything minimal at the moment. I'm just using actually something maximal, a co-fiber replacement. Right. So what are some other things going on? So we're continuing to work with Clemens on the chain level, which gives us I mentioned that result, which gives us cellular chains and string topology and all this kind of fun stuff. There is a generalization of the plus construction. I'll get back to that. There's an expansion of these Hopf algebra structures we can look at with the student of mine, Yang Mo, and that if we figure this one out, that also will connect to Tanakian categories and quantum groups, in a sense, the way that they're introduced in Manin's book. You can connect this directly to quiver series. That's already done in the representation theory paper. And you can then in class ask about stability conditions and wall crossings. And we know what that is. That's contracting and expanding an edge. And that's also related to higher Siegel spaces. If you want to have, I put this in, I think probably the slides will be shared. And then this is just a link to my webpage. So if you click on that, you'll see when I say the 2019 paper, you'll see what the 2019 paper is. All right. And that's the end.
Thank you, Ralph. Are there lots and lots of questions? In the chat, there is just thank you, Ralph, and lots of clapping. No?
I did promise master equations. So here's the master equation slide. So the point is that it depends on what Feynman category you're looking at. Then there is a differential, which is also governed by this diamond condition. Then you can do the Feynman transform. That will give you a free thing, but it's free. It's and the question is if that is BG. So we can write the master equations you find in physics, just as this thing about universal operations and that you get from this presentation of the Feynman category and the differential which you get from this presentation. So if you start with an operad, you get the master equation with the pre-Lie. If you take an odd Lie, so if you take a cyclic operad, you'll get an odd Lie structure as the algebraic structure, and the master equation will be this. And you see that there's just a bracket. This has a direction, this doesn't. If you take a modular operad, you get the quantum master equation. If you take a proprad, you again get this pre-Lie structure. If you take a wheel proprad, you again get something like a quantum master equation, but with a pre-Lie structure. And if you take a wheel prop, you again get actually the nice DGBV structure. And this is collected together from papers from Gerstenhaber, Kapranov, Manin, Merkulov, Valette, Baranikov, and they're all contained in this general paper. So this table is contained in the paper with Javier Zuniga. And then this is sort of wrong. So this is not, sorry, I didn't want to do that. So what happened? I needed those. Well, now it went away. That's fine. So sorry, this is actually, sorry, I can't deal with this. All right, sorry, this is in the Feynman category paper, the generalization. This one is basically in KDZ where we do this. So that answers the question for the master equations.
Well, I guess so. So I had, well, just an almost infinite number of questions. Can I just ask probably one obvious thing? You seem to have covered, all the territory. One thing I wanted to know about, which I've always been wondering. So you have, tell me if I'm wrong, you have a nice way of now talking about operads and non-sigma operads, so symmetric and non-symmetric operads in the same language. But there's other people have been talking about other groups, not just SN. Can you do something? Is there something between? Do you understand the things that come between SN and the trivial action?
I don't think there's much between Sn and the trivial action. There is something higher. So I mean, there are three things. So the first point is this V. If you look at this V tensor, this will have sort of wreath products with some groupoid, right? So you'll see those that come up directly.
Yeah,
This is why you're going to see
That's probably what I meant. Yes.
So there's this cross thing. So but it loves above Sn. So I mean, the point is you can do without Sn. So in the n and non-sigma, if you want, then you can just have the groupoid itself. So you can have those. So yes. Yeah. And then sort of the maybe it's only 2 points. Then the second point is that you could do, I mean, instead of looking at Sn, so if you look at the cross and placial things, these are, for monoidal, but they're braided monoidal, so this is symmetric. And this will be braided. So you can look at certain crossed groups. So this is for placing Sn. So you say you have nothing, then it's just monoidal. Mm-hmm. Then you can go to Sn. So there are two parameters you can play with. You can play with this groupoid, so that's in between if you want. But then sort of for monoidal categories, there's nothing in between, right? You can go from monoidal to symmetric monoidal. I don't know if you want to call braided monoidal in between. I mean, that's up to you how you want to say that.
No, I was thinking of things like cyclic or dihedral.
Right. So you can look at dihedra, and this list goes on. So if you have a monoidal category type of this type, I mean, they're not all cross simplification groups work this way, but if you have an associated notion of monoidal category like symmetric monoidal, dihedral monoidal, like in Lode, the ones you can find, then you can of course run the whole theory in that framework.
Anyone else got questions?